Let's now talk about physical properties of halalkanes. Halalkanes are polar compounds, and that is a factor that determines a lot of their physical and chemical properties. And so if we have a methyl halide, then this bond between carbon and halogen will have a dipole, and this dipole will be proportional to the product of charge and bond length. And charge is really related to the difference in electronegativities. And so when we look at the electronegativities of different halogens, you'll see a trend that they go from fluorine to chlorine to bromine to iodine, and the values are 4.0, 3.5, 3.0, and 2.7. Okay? However, the bond lengths increase in the opposite order. So Ci bond is the longest with 2.14 angstroms, and you go to CBr, which is just under 2. Then CCl bond is 1.78 angstroms, and then finally carbon-fluorine bond is relatively short, 1.38 angstroms. And so the product of these two values, whose trends are opposite, will be sort of a mixed, sort of give us a mixed signal. So the dipole moment varies in a fashion that is not immediately obvious. So the highest dipole is that of carbon-chlorine bond, and the next one is carbon-fluorine bond. Finally, carbon-bromine bond, and carbon-iodine bond is the least polar one. Okay. In terms of molecular dipoles, we already talked about the fact that dipoles are vectors, and then their addition takes account of the direction as well. And so as a general rule, if we have a compound with the formula CX4, all dipoles will cancel each other out, so the overall dipole moment is 0 dBs. And for compounds with the formula CHX3, this dipole moment in general is 1.0 dBs, and CH2X2, this goes a little larger, about 1.5 dBs. And finally, the CH3X compounds are the most polar ones, and it's about 1.8. Again, it's a general value that you don't really need to remember, but it's an important point that the monosubstituted halalkanes are actually the most polar ones. Okay. When it comes to boiling points of these compounds, they are determined by London dispersion forces and the dipole-dipole interactions. The dispersion forces, as you remember, are forces that hold all molecules together and are proportional to surface area, and while the dipole-dipole interactions are holding together polar molecules, and they're related to differences in polarity between different molecules. Perhaps counterintuitively, dispersion forces are the main contributor to the boiling point differences, because halogens, especially larger halogens, are very large atoms, so they increase tremendously the surface area of these molecules and allow them to have much greater contact area. And dipole-dipole interactions come in on the second time. And so if you look at the structure of various halalkanes, these are all propane derivatives. So with fluorine, the boiling point will be 3 degrees Celsius. If we switch to chlorine, this will be 47 degrees Celsius. Bromine gives us another almost 30 degrees, so this is 71 degrees Celsius. And finally, iodine is 102 degrees Celsius. So this is a very steady rise. And just like in alkanes, we see that the branched compounds have lower boiling points. And so if we have N-butyl bromide, the boiling point here is 102 degrees. But if we have P-butyl bromide, the boiling point here is much lower, 73 degrees. Another factor that we need to consider with haloalkanes are the densities. Halogens are heavy elements. They make their derivatives relatively dense, and so many of the haloalkanes are more dense than water. The density of water is 1.0 grams per centimeter cube, which is a little unusual because most organic compounds are actually less dense than water. And so, and especially all hydrocarbons are less dense than water. In terms of these rules, all alkyl bromides and alkyl iodides are more dense than water. Alkyl fluorides are less dense than water. And alkyl chlorides, which are probably the most common ones, are mixed. So if we have one chlorine, they're going to be less dense. But if we have multiple chlorines, they're going to be more dense than water. In other words, chloromethane is less dense than water, but and it's a gas. But all the liquids, such as dichloromethane, chloroform of carbon tetrachloride, are heavier than water, and are therefore the lower layer when you do the extraction with salt.